Okay, today we are going to be continuing our look at simple population models in discrete time. We're going to be moving on to logistic growth. Can I have a show of hands who's heard of logistic growth before? It's got kind of a little bit, I think. Okay. So the key difference, I guess, is before we were thinking about exponential growth, these populations could just explode off to infinity. Now we're going to be thinking about ways in which we might constrain that, okay? So by the end of the day, you should understand this concept of logistic growth and how it relates to population growth in real populations, the idea of nonlinear as opposed to linear sets of equations, density dependence rather than density independence, and then thinking about how we might start to analyze these in a bit more detail, looking at things called steady states or equilibria, and then thinking about the stability of those equilibria. So what happens in the long term in these models? So you should be able to construct these simple density-dependent population models in discrete time by the end of today. Okay, so if you recall from last week, we had a general form for a single species discrete time model. So population size, n, in time step t+1. So this could be, remember, days, weeks, months, years, generations, some sort of projection interval. Our population size n at time point t.1 is some function f, little f of nt, and this is the net growth rate or growth ratio. And then we can also write this for population models as our population size times capital F of nt, where that capital F is our net per capita, so per individual growth rate of population. Okay, so we looked at linear population models because we could write this capital F of n as just some constant, which we called lambda. Okay, and this gave us exponential growth or exponential decay. So now with our nonlinear population models, this capital F of n is no longer just a constant, it's going to be some function of n. Okay, so this makes it density dependent. So why might f of n be density dependent? Anyone? Yep.
If there's like more population, there's more to like, I guess there's more ways to affect that larger population because there's just more there.
Yeah, so what do organisms need to grow, to survive, right? They need some sort of resources. So typically, if you've got large populations, you've got more individuals competing for those resources, then the growth rate is going to be reduced. Either that could be the death rate increasing, or it could be the birth rate decreasing, or a combination of those two things. Okay, so limited resources. When I say resources, this is also could be seen in a very broad sense. Resources could include things like space, habitat. That is essentially a resource. It could be, and this is often termed as overcrowding. So there's a physical sense of overcrowding in space. Resources can also include things like mates. Okay, so you might have more mates because the population size is larger, but the mate availability might be lower for reasons due to competition. So we refer to this type of competition as intra-specific. And when we come on to do multi-species models, we'll also talk about inter-specific competition, so competition between species. Okay, so how do we construct one of these nonlinear models? If you remember, when we constructed the model the other day, we had nt+1 is going to be our current population size nt plus delta nt, so some change in the population size. So we can write down a similar form here. If we just focus on this part here, this is exactly the same as the linear model that we had the other day. Okay, so we've got our present population size, we've got a birth term, so B is our per capita birth rate. So our total number of births is going to be B times by n at time t. And then here we've got a death rate. And this is going to be the total number of deaths is given by our per capita death rate D1. times by the total number of individuals in the population. And if you recall, we said that B has to be greater than or equal to 0, and D is a probability, so that goes between D1 goes between 0 and 1. Okay? So the key difference is this last term here on the right-hand side, where we have density-dependent deaths. So what's going on here is that it kind of looks the same to start with. We have some parameter D, D2 here, times by our population size. So that gives a per capita element to this death rate. But then we multiplied this by our population size again. So what happens if we try to simplify this a little bit? We can write this as NT plus, take out a factor of NT for the rest of the terms here. I have a B minus D1 minus D2 times NT. So before, when we did this factorization, there was no NT here. So our lambda previously was just this bit here, and that was a constant. But now this is going to be a function of n, because there's an n inside this bracket. We could just leave it like that. Logistic growth models are usually written in a slightly different form. So if we notice this B minus D1 here, but B is just a number, D is just a number. Okay, so we can write down a number that is equal to B minus D. So if we let, different color here, I'm going to let R equal B minus D1. Means I can write this bit here just as R. And then I want to get rid of this D2, just because I'm writing it in a slightly different form here. And I'm going to let K equal R over D2. So there isn't currently an R here, but I've got a D2. So if I rearrange this, this means that D2 is equal to R over K. So I can write R minus R over K, because this D2 I've just replaced with an R over K. So it looks like I'm making things more complicated to start with. So I kind of am. And we have my NT here. There's now an R here and here. So I can pull that out of this model, out the front. So now we're going to have NT plus RNT. That's by 1 minus NT over K. And this form here is usually how you'll see a logistic growth model written. Sometimes it just jumps straight to this in like a textbook. And it's not necessarily clear where this R and this K come from. What are their actual meanings? I'll talk about this in a moment. But here is showing how they're derived from the idea of just births, density-independent deaths, and density-dependent deaths. Okay, any questions so far? Nope. Okay, so why have we written it in this way? Well, this R is equal to B minus D1, so the difference between births and density-independent deaths is known as our intrinsic growth rate. So this is basically saying if we ignore any density-dependent effects, any of those density-dependent deaths, what would the population grow at? It's also telling us when there's no one in the population, or the population is very, very small, approximately what is the growth rate of that population before density dependence starts to affect it. So that's why we call it an intrinsic growth rate. And then this K, referred to as the carrying capacity. Has anyone heard of the concept of carrying capacity before? Yeah, a couple of nods. So the idea of a carrying capacity is basically saying how many individuals can the environment support. So depending on the amount of resources available, what's the maximum population size that can be supported? So yeah, often you'll see a logistic growth model written something like this form. The idea of an intrinsic growth rate or a carrying capacity, it's not really clear, especially carrying capacity, like where that actually comes from. But the carrying capacity depends on this relationship between births, deaths, and density-independent depths that are independent and dependent on density. Kind of good to know that it isn't just plucked out of thin air as a number. It does depend on those underlying processes. Okay, I want you guys to have a go at sketching this f of n here, 1 plus r times by 1 minus nt over k. So this is our net per capita growth rate. Have a go at sketching this. One of the reasons I want you to have a go at sketching this is because in a lot of courses, I find that students are not very good at sketching graphs. If you're able to sketch what a function looks like, it can often give you a lot of intuition as to what's the underlying behavior of a model. Okay, so we're going to be doing quite a lot of curve sketching at various points. Okay, so how do we go about doing this? If you're not familiar with how to sketch curves, good things to think about. I'll think about when does it cross the y-axis? So f of 0. When does it equal 0? So think about, for example, what happens if you substitute k into this for nt? So set nt is equal to k, what happens? So think about what happens when it's crossing the axes. That kind of gives you points to anchor a function down, right? You can also think about what happens maybe when you can think about the derivative. You can think about what happens when, in this case, n gets very large, or when it gets very small. Kind of giving away that small bit here. But thinking about, anchoring our function down by different points, or what happens when it gets very large, it tends to infinity, or it tends to a very small amount, will help you to sketch that graph. Okay, so have a go at that the next few minutes. Okay, let's see how you guys got on. So first of all, can anyone tell me what f of 0 is going to be? So if we substitute 0 in here, ahead of whispers, sounded right? 1 plus r, yeah. So this just goes to 1, and we have 1 plus r. How about f of k? I realize I might have been slightly misleading when I said. Yeah, so if we said if n now is k, then we're going to have 1 minus 1, so it's going to be 0. We could lose the r, and we just end up with 1. Okay, so what does this look like then? Well, what else can I tell about this? I can tell that this is linear, okay? So this is just a straight line. There's no n squareds in this, right? There's just an n by itself, and it has some things that multiply it, okay? So it's going to be a straight line. So that means that I just need 2 points to figure out where it is, or what it looks like. So I know it crosses the vertical axis at 1 plus r. So I'm going to draw a little dashed line here. So I know it crosses here. And I know that when n is equal to k, we're at 1. I also know that r is greater than 1, greater than 0, sorry. So I know that this line is below the other one. So this is the line f of n is equal to 1. So I know I cross here, and I know when n is equal to k, some value along here, I know I cross there as well. So because it's just a straight line, okay, connect these things up. It crosses the axis somewhere else. I'm not going to worry about that for now. Who ended up with a straight line that looked something like this? Yeah? Okay, great. Okay, let's divide this up a little bit more and think about what it actually means then. So I'm going to split this into some quadrants here. So if we think about this net per capita growth rate, if each individual in the population is producing, on average, 1 surviving individual in the next generation, if they're producing more than 1 individual, then the population is going to be growing, right? So that means that when we're above 1, so in this region here, we're going to have growth. The population is going to be growing. So that means when n is between 0 and k, so now when we have our net per capita growth rate less than 1, that means that on average, each individual is producing less than one surviving individual in the next generation. So that means the population is going to be shrinking. So in this region here, we have decay. So we see that as n varies and we pass through when f of n is equal to 1, we're going to switch from population growth to population decay. So this brings us onto the idea of a steady state. You might also hear it referred to as a fixed point or an equilibrium, basically all the same things as far as we're concerned. So a steady state occurs when our population size in the next time point is equal to the population in the current time point. I'll call this n star for some value n star. We don't know yet. So in other words, if we think about our net growth rate, not our net per capita growth rate, but the net growth rate little f, we're basically just saying we want to solve this equation here. N star is equal to f of n star. Did you have a question, or were you just thinking through? Okay, so let's think about what are the steady states of this logistic growth model? Okay, so how do we go about solving this? If our little f of n is going to equal everything that we had on the right-hand side. So n plus Rn, that's by 1 minus n over k. And at steady states, f of n star is equal to n star. So that's just the equivalent of, I'll cheat a little bit here and just set this equal to n star, rather than writing it all out again. Okay. So how do we solve this? Well, if you know, first of all, that there's an n in all of these terms. So one thing I could do is I could assume that either n star is equal to 0. If n star is equal to 0, then everything on the left-hand side is 0, everything on the right-hand side is 0, so it balances, okay? And we refer to this as a trivial or extinct population. Okay, pretty obvious. Nothing happens if no one's there. So that's one of our equilibria. And often you'll find this in a population model. We can't always assume this is definitely the case, but usually you'll have a trivial equilibrium like this. Or, what's the other alternative? Well, the other alternative is that n star is not 0. If n star is not 0, then we can divide through by it, okay? If it was 0, we couldn't divide by it. But we've eliminated that possibility as one option. Now we're going to assume n star is not equal to 0. I can write it properly. In which case we're going to have 1 plus r, that's by 1 minus n star over k is going to equal 1. So all I've done is divide throughout by n star. Okay, there's a 1 here and a 1 here, so I can just subtract 1 from each side. So that means that r times by 1 minus n star over k has to equal 0. Now the r is a positive parameter. We're assuming that births are greater than deaths. So r is greater than 0. So that means the bit in the parenthesis has to be equal to 0. So when is this equal to 0? Yep, so when is that? N star is equal to k, okay? So this tells me, yep, n star over k has to equal to 1. So n star is equal to k. Note, this is our carrying capacity. So we're basically saying, in this model, there are two steady states that we can end up at. Either the population goes extinct, or we're at our carrying capacity. Those are the only places that we can stay. If we start there, we stay there. So let's think then about what it means for us to say, like, what happens in the long term? What's the stability of these things? Whenever we talk about stability, basically think long term. So after everything settles down, what happens in the super long term? The other way of thinking of this mathematically is as t tends towards infinity. So typically we want to know, are populations going to grow or decay? Are they going to move towards a steady state or away from a steady state? Okay. And so just because we have something that's a steady state doesn't mean that we'll move towards it. It doesn't mean it's stable. So we talk about stability or instability. So if something is stable or unstable. And this uses something called linear stability analysis. So what this is really saying is saying, if we start very, very close to our steady state, do we move away from it or do we move towards it? If it helps to visualize this, you can think about stable and unstable steady states like this as being like a valley or a hill. So if you imagine you start in this valley and you have a ball at the bottom of this valley and you move it a little bit up here or a little bit up here, it will move back down towards the center point of this valley, okay? So you move away, but then we come back again. So this is this idea of it being stable. Whereas if you perch a ball right on the top of a hill, if you do nothing to it, it stays there, right? It's perfectly balanced. But if you give it a little nudge in either direction, it will keep moving away. It doesn't come back again. So this would be unstable. So this is basically the same thing as happening in our population models, okay? We either have a stable steady state, where if we move away from it, we come back to it, or we have an unstable steady state, whereas if we move away from it, we don't come back to that point. So how are we going to actually analyze this? Well, the idea here is that if you zoom in on anything enough, it basically looks linear. Okay, so think about the Earth being a globe, right? If you're far out in space, it's clearly a globe. But if you zoom in enough, for example, this room, this bit of room, it's pretty much flat, right? Even, over fairly large scales, things look flat. And it's the same idea in these nonlinear systems. If we zoom in enough, if we treat things as being local enough, then we can get rid of our higher order nonlinear terms, which are difficult to deal with, and just focus on the linear stuff. And that tells us only what's happening very locally, but usually that's enough. Okay. So that's the idea. So how do we go about doing that? Well, we're going to do a little change of variables here. We're going to set this little n of t to be our population size at time t minus our steady state value n star. Okay. And this is referred to as a small perturbation from our steady state. So what we're doing is we're essentially now modeling whether we're the size of this movement here. If I zoom in here, this size here, how much we've moved away from our steady state, is going to be this little nt. And so we want to know if this perturbation grows or decays with time. So if this perturbation, if this little nt gets bigger and bigger and bigger, that means that we're not going back towards n star. The difference between capital NT and n star is getting bigger, therefore we're not moving back towards it. If it goes to 0, then it means that NT is tending towards n star. So that means the difference between our steady state and the population size at a given time is getting smaller. So we're moving towards it. Okay, so let's think about the dynamics of this perturbation. So what's it going to be in the next time step? So nt plus 1, little nt. Well, we just take our population size at time t plus 1, and this n star is a constant. It's just a number, okay? 100 individuals, say. We just stay there. Now, if you remember, our nt plus 1, we just defined to be some function f of nt. So that means I can write this as f of nt. And I can also write this as f of n star, okay? The reason we can do that is because n star is equal to f of n star. That's what it means by definition for it to be a steady state. Okay, what else can we write down? Well, from this equation up here, we can just do a little bit of rearranging. and take the n star to the other side, and we can write this as n star plus little n of t is going to equal capital N times t. That's just moving the n star to the other side. That means I can substitute into here f of n star plus little nt, and we've still got this minus f of n star here. Am I going too fast or too slow? Does anyone seem to slow down? If I don't hear any feedback from you guys, I assume I'm going at the right pace, okay? So it's totally fine if you want me to explain things again. Just let me know if I'm going too fast, okay? Otherwise, I just assume you're understanding everything. Yep. Good job. I said it's totally fine for me to explain it. Okay, so all we're doing here is we're seeing the dynamics of this perturbation, if you recall. We're seeing, are we moving away or are we moving back towards this steady state? So is this little nt growing or decaying? We're just using our rules of these functions here. So what does it mean to have a population model? It's just some function of the previous time step. What is a steady state? Well, that steady state is just equal to the growth rate, or the function of that growth rate, the growth rate of that steady state. And here, this is just using our definition of what our perturbation is, okay? Everything else just follows through these equations. We're just substituting things in. This is where it gets a little bit more complicated. Here, we're going to do a Taylor expansion. And this is where this idea of linearity is going to start to come in, okay? Now, if you're familiar with Taylor expansions, this is a way of approximating what the value of a function is close to a particular point, okay? So this is just essentially a formula. What it says is that this bit here, we can expand as f of n star, so the value of this function at n star. And if we're staying fairly close to it, we add on the derivative of this function at n star times by this little nt. This is just the formula for a Taylor expansion. You don't need to memorize this. This is showing you where this all comes from. Okay. And we still have this minus f of n star on the end. Now, if you note, we have a plus f of n star and a minus f of n star, so those two things cancel each other out. So what we're saying now is that the change in this perturbation, whether it grows or decays in the next time step, is going to equal roughly the derivative of our net growth rate at our steady state times by however big our perturbation is at that time. Now this f prime of n star is just a number, right? And f is a function. And just like if you had a curve or a line, you found a point on that curve or line, you take its derivative at that point, it just gives you another number, okay? So this f prime of n star is just a number, which I'll call lambda. Can anyone tell me anything special about what this is? First of all, does it look familiar? Okay, good nods. Can anyone tell me what this was? This was an equation for, if I get something to go down, I don't want to put it on the spot.
Yeah, it was for the
Exponential growth, exactly, yeah. So exponential growth, and the key thing about the exponential growth or decay is that this was linear. Okay, so this is a linear model. So we've transformed this difficult nonlinear problem into a simple linear problem. We know how to deal with linear models. We did that last week, right? Things either blow up to infinity or they decay. I should say exponential growth or decay. There's a slight caveat here when lambda is positive. We'll get on to this in a moment. Before when we dealt with population sizes, we restricted ourselves to the case when lambda was at least non-negative. Okay. Because otherwise you'd suddenly go from a positive population to a negative population, which you can't have. Now we're not dealing with population sizes per se, we're dealing with this perturbation. So the perturbation, the change from our steady state can be positive or negative. So our lambda doesn't have to be positive anymore. That if lambda greater than 0 is just saying it's related to that exponential growth of decay when it is positive. Okay, what does all of this mean then? If we're neglecting those higher order nonlinear terms, we've transformed our nonlinear population model, which is difficult, into a linear population model, which is easy, at least around close to our steady states. And so we can summarize the behavior of our perturbation as follows. So we find this lambda by taking the derivative of our net growth rate, little f, at our steady state, and then we see what value it has. So let's deal with the ones we know about first. If lambda is between 0 and 1, our solution is going to look like n times t, perturbation at time t is going to equal lambda to the t times by whatever the initial size of that perturbation was, n0. So this will tend towards 0 as t tends towards infinity, right? If lambda is between 0 and 1. So that means that we have something called monotonic decay for our perturbation dynamics. We just decay towards 0. And then we say that our steady state is therefore monotonic stable. The monotonic means that you just tend towards it from one side. Okay, that's what monotonic means. And it's stable because you're moving towards it. The size of this perturbation is decay. Okay, what about if lambda is greater than 1? Well, here we're going to have exponential growth because this lambda of t is going to be something greater than 1 taken to the power of t, and t gets very large, so that's going to keep growing, just like our population sizes that grow exponentially. So here we say it's monotonic unstable. So this is just like the one where we have a ball on the top of a hill. As we move a little bit away from its starting point, we just keep moving away from it, and we keep moving away in one direction. So it's unstable, and it's monotonic because we're moving away in one direction. Okay, so those are essentially the things that we understand so far. Did you have a question?
Oh, I was just wondering if it's just describing if we converge toward that.
Essentially, yeah. Well, are we moving towards our steady state, or are we moving away, just like the balls in the valley or on the hill? Yeah. Okay, so yeah. It's because, so the general solution of the perturbation is this equation up here. And so if lambda is less than 1, when we take lambda to the power of t, it's going to be something less than 1, like a fraction between 0 and 1, taken to the power of t, so half times half times half times half. It's going to get smaller and smaller and smaller. And so that perturbation goes to 0. Whereas if lambda is greater than 1, then it's going to blow up. Yeah. Okay, let's think about the slightly more complicated scenarios now. What happens if lambda is negative and between -1 and 0? Well, we've still got the same equation up here. This still tells us the solution. My screen's just died. Hopefully that will come back. We're still going between, we've still got this equation up here, but now because lambda is negative, for every value of t that is even, we're going to be doing something like, say, -1/2 squared, which gives us a quarter, right? If it's negative, sorry, if it's even, then we're going to end up with a negative value. So for t even, we end up with something that's positive when we do lambda to the power of t. And when t is odd, lambda to the power of t is going to be negative. So that means we're going to be going either side. The perturbation is going to be going from positive to negative, positive to negative. So it's oscillating, right? But it's still between 0 and 1 in terms of its magnitude. Okay, so although we might be going from, say, -1/2 to 1/4 to -1/8 to 1/16 and so on, it's still getting smaller. So we say that this is oscillatory decay. So it's oscillating, but it's still decaying. And therefore, we say that our steady state is oscillatory stable. Okay, so oscillating, but it's still stable. Note that in both of these cases here, they're stable. It's just that one of them is oscillating, one of them is monotonic. So when lambda has absolute value less than 1, it's always stable. If it has absolute value greater than 1, then it's going to be unstable. Okay, the last scenario to look at is what happens if lambda is less than -1. Well, this is going to be like the case just now where things are going to be oscillating because this lambda is negative. But now we're going to be growing. So if we started off at, we end up with lambda is -2 to start with, then when t is positive, sorry, when t is even, get my positive and negative stuff. When t is even, we're going to go from, say, -2, then up to 4, and so on. We're going to be flipping back and forth. So we're still oscillating, but we're growing. Okay, the perturbation is growing, it's not decaying to 0. So this is oscillatory growth, and so we say that our point is oscillatory unstable. So really, we care about finding about the absolute value of lambda and whether it's positive or negative. That will tell us the dynamics. This bit at the bottom that I put as a footnote is just a little bit of extra stuff that to say, we can ignore these higher order terms. But we'll move on. Okay, so let's think about what is the stability of each of our steady states. I'll work through this with you guys, okay? So we're going to call this function here, this is our little f of nt, what we had to start with. And recall what we need to do is we need to find our derivative of f with respect to n. So if we just find this to start with, and then afterwards we can work out what our, afterwards we can then substitute in our n stars, okay? So we find the general form. So we can take out this nt, first of all, if we take a derivative, we're going to have an nt times of 1, so that's just going to give us a 1. We're going to have an nt times by an r times by 1 here, so that's going to be 1 plus r. And then here, we're going to have a minus r times nt squared over k. So when we take our derivative with respect to n, we've got a quadratic. So the 2 comes to the front. So we're going to have -2 times by r n over k. So we reduce the power by 1. This is just our power law expanded out. Okay, so let's think about what happens when f is equal to 0. Sorry, when n is equal to 0, we have f of 0. We're just going to substitute 0 into this line above, okay? So f prime of 0, this bit in the brackets just disappears, or the last term with the n disappears. So we're going to have 1 plus r. So what do we know about this? Well, we said to start with that r was going to be positive, so this is always going to be greater than 1. So we can say that this is going to be monotonic unstable. Why? Because this is just my lambda. If I go up here, I see that lambda is greater than 1. This is monotonic unstable. This is at n is equal to 0. Then if we think about at n is equal to k, just substitute this in now. So we're going to have a k over here. So we have -2rk over k, so the k's are going to cancel out. So we're going to have 1 plus r minus 2r, which is going to equal 1 minus r. So this, now the behavior is going to depend on the value of r, okay? So if we think about what happens if r is, say, if r is between 0 and 1, so if 0 is less than r is less than 1, then this lambda is going to be between 0 and 1, so it's going to be monotonic stable. if R is between 1 and 2, then lambda is going to be between -1 and 0. So it's going to be oscillatory stable. And if R is greater than 2, we're going to be having, say, 1 minus 3 is minus 2. Then this is going to be oscillatory unstable. So we see the dynamics of the system depend, around this carrying capacity, depend on this intrinsic growth rate. And as this intrinsic growth rate increases, we go from something that approaches our carrying capacity in a stable monotonic way to being something that oscillates but is stable, so we'll tend towards it in the long term, to something that's unstable and we don't tend towards it. So as we increase the growth rate of this population, we can have this kind of slightly counterintuitive scenario where things become less and less stable. You might, intuitively think, oh, if the growth rate of a population increases, it will start to become more stable, right? It will tend towards its carrying capacity because it's got more chance of getting that. But no, if R is greater than 2 here, it's oscillatory unstable, and so it goes all over the place. Yes?
Just to be clear, for those two values there, you're calculating f prime of 0 and f.
Oh, sorry, yes, there should be f prime. Thank you for pointing that out. Yeah, thank you. Do shout out if I have any typos. So, and same with the completed notes. Because it's the first time this course is being taught in this format, that like typos will creep in. I am only human, but I'm more than happy to correct. So thanks. Okay, so we've just got a few minutes left. So just think about that interpretation. How does the intrinsic growth rate affect these population dynamics? In fact, rather than writing everything out, I'm just going to throw everything up here. Here we are. So what do we have then? So if that R is between 0 and 1, so if we have a relatively low intrinsic growth rate, remember this R is just the difference between bursts and the density independent deaths. So this is saying there's not a big difference between individuals being born and the rate at which they're dying, at least in that intrinsic death rate. What this says is it's monotonic stable, so that means that any non-zero population will tend towards that carrying capacity K. Okay. If we have, say, if we just keep the density independent deaths constant and start increasing the birth rate, then this R is going to increase. And when we cross between R is 1 and R, sorry, when we cross over between R is less than 1 and R is greater than 1, we suddenly have our population will start to oscillate. So we'll be moving either side of our carrying capacity. Essentially, we're overshooting it, and then individuals start dying, and then we undershoot it. And then individuals can be born again, and so we go like that. So we'll tend towards it eventually, but we keep missing it to start with. Okay, so it oscillates, but it's stable still. Here, we've increased the birth rate even further, but now the population is oscillating, but it's really overshooting and really undershooting. So, like I said, it gives this kind of counterintuitive idea that as we increase the birth rate in a population, it can have a destabilizing effect. It's not necessarily good. If these oscillations get too big, it could overshoot really, really far, and then there's just, say, twice as many individuals in the population as there should be. None of them can get enough food, and then they all die. So you can have scenarios where if you get a sudden massive expansion of population because been a glut of resources one year, but then an absence of resources the next year, say, and so the birth rate was high. Now it's going to suddenly drop down, and we end up with the population crashing. So we sometimes, this is one of the reasons to do models like this, is because even a very simple model can tell you something fundamental about biological populations. That in this case, we've got a kind of paradox that increasing, say, the resources for a population isn't always necessarily good, because it could cause you to go into these oscillations, which makes the population crash. Okay, any questions on anything I've gone through today? Yes, Scott.
All right, so then what would the bond theory, like, what would it look like if the water is stated to
That is a very good question, and kindly nicely leads into the next lecture. So next time we're going to be talking about, I believe, let me just double check. We're going to be talking about cobwebbing. Okay, so we kind of get into it, and then the next lecture after that, we're going to be talking about chaos. So this is a very famous model, often referred to as a logistic map. And we see that as you start to increase this R and it goes to these larger values, things become very unstable, and you can get, first of all, periodic cycling. So maybe it just fluctuates between 2 values, and then it fluctuates between 4 values, and then 8 different values. And then eventually everything goes chaotic. It might die out. It might just sort of just go around at any value, basically. It's still deterministic, but we get this element of unpredictability. Has anyone heard of the butterfly effect? Yeah. So this idea of chaos and butterfly effect comes from these sorts of very simple models. And so, yeah, it depends exactly on your value of R. Things eventually just kind of blow up and go crazy. It's one of the reasons why these models aren't necessarily the greatest models. They apply in some circumstances, but aren't the most general models for populations, because they have these instabilities that come out of them eventually. And you don't get these in one-dimensional continuous time models, which we'll talk about in next week, I believe. Yeah, so actually the self-study problem, there's a Jupyter workbook that's posted on Canvas, which should allow you to explore the dynamics of this model yourself. So I think it's good if you can intuit exactly what's going on. You know, I've described mathematically, this is the stability of this point. You can use the workbook to just put in some different values of R as you increase from these low values up to things greater than 2, and you'll see what happens. Okay. Any other questions? Okay, have a good week. I will see you guys on Wednesday.